If the engines on your flight died instantly, right now, how far do you think you could travel before hitting the ground? A mile? Maybe 2? Try 100. A commercial airliner without engines isn't a falling rock. It is a highly efficient 300-ton glider. From cruising altitude, you have 20 minutes of flight time to find a safe place to land. But how is that possible without power? Today, we're breaking down the invisible physics that keep you in the sky, why air acts like concrete at high speeds, and why gravity is actually the pilot's best friend. The coasting situation. Lift versus thrust. To understand why planes don't fall, we have to separate two things that you may have heard one time when you were listening to your friend obsessed with aerodynamics: thrust and lift. Simply put, think of a bicycle. When you pedal, that's thrust. It overcomes the friction of the road and the air to keep you moving forward. If you stop pedaling, do you instantly tip over? No, you have momentum. You coast. A plane is the same, but with one major difference. On a bike, friction slows you down until you stop and fall over. In a plane, you can trade height for speed. Gravity wants to pull the plane down, but the wings want to push the plane up. If the pilots point the nose down just a tiny bit, gravity actually acts like a backup engine. It pulls the plane forward through the air, keeping the speed high enough for the wings to keep working. This is called the glide ratio. A typical commercial airliner has a glide ratio of about 15:1. That means for every mile it drops, it travels 15 miles forward. If you lose your engines at 35,000 feet, you have about 20 to 30 minutes of flying time to find an airport. So, rule number 1, engines are for speed and climbing. Wings are for staying up there. As long as you have wings and speed, you are flying, not falling. The invisible solid, air density. So this begs the question, why do wings work at all? How can this invisible gas hold up a 300-ton metal tube? It helps to stop thinking of air as a gas and start thinking of it as a fluid, like water. At low speeds, air is flimsy. You can walk through it easily. But at 500 miles per hour, air molecules don't have time to move out of the way. They compress. They become hard. At cruising speed, the air beneath the wing is acting almost like a solid surface. This brings us to one of the most iconic shapes in engineering, the airfoil. The curved top and flat bottom force the air to behave differently. The air on the bottom pushes up, simple impact, generating higher pressure, while the air on top is stretched out, creating low pressure. This pressure difference effectively sucks the wing and, by consequence, the plane upwards. So the plane isn't really floating. It is being sandwiched between high pressure below and low pressure above. As long as the plane keeps moving fast enough to make the air hard, physics literally forbids it from falling. The only way to fall, the stall. There is, however, one way a plane can fall. It's called a stall, and it has nothing to do with the engine. It has to do with the angle. If a pilot pulls the nose up too high, the air can no longer stick to the smooth curve of the wing. It detaches. It becomes turbulent. This is the critical angle of attack, which is usually defined between 15 to 18 degrees from the horizontal. When the air separates, the low pressure zone on top collapses. The wing loses the one thing that defines it: lift. Even though the shape hasn't changed, its function has. It is no longer an airfoil slicing through the air. It becomes just a heavy piece of metal fighting gravity and losing. But here's the cool part. Engineers designed the plane to want to fix this. Most planes are naturally stable. If they stall, the nose drops because of where the weight is placed. When the nose drops, the plane speeds up. When it speeds up, the air flows smoothly again. The wing starts flying again. The plane literally wants to save itself. Redundancy. Okay, so the physics are safe. But what if the parts break? What if the cable that connects the pilot's joystick to the wings snaps? This is where we get into redundancy. In engineering, 1 is a dangerous number, so planes use the rule of 3. So planes use what we call triple redundancy. We don't just build 3 hydraulic systems, we physically separate their plumbing. The lines are routed through completely different zones of the airframe, ensuring that a single localized event, like a bursting engine, cannot physically reach all 3 lines at once. If System A fails, System B takes over. If B fails, System C is there. Even if you lose all electrical power, there's a little device called a ram air turbine, basically a little windmill that drops out of the bottom of the plane. The speed of the wind spins the propeller, generating enough electricity to power the essential flight computers. It's a literal windmill for survival. Structural margins, the 150% rule. Finally, let's talk about the structure itself. You might look out the window, see the wing shaking during turbulence, and think, that looks flimsy, it's going to snap. But to an engineer, that flexibility is the strength. And to prove it, manufacturers have to perform what is essentially a medieval torture test. It starts with the limit load. This represents the absolute worst-case scenario the plane is expected to see in its entire service life. We're talking about a once-in-a-history storm combined with a hard maneuver. At this level, the rules say the wing must take the punishment and return to its original shape with 0 permanent damage. But they don't stop there. Aviation regulations require a safety margin on top of the worst-case scenario. They push the wing to 150% of the limit load. This is called the ultimate load. The requirement is simple. The wing must hold this insane weight for at least 3 seconds without failing. Without failing doesn't mean it stays pretty. At 150%, the metal might stretch or buckle permanently, and the plane would never fly again. But the wing effectively stays attached. The passengers survive. Often, engineers will keep going until the wing actually snaps, just to see how much extra margin they have. When you see those photos online where the wingtips are touching the ceiling, that is usually a test to destruction in a lab. So, if you see your wing bouncing in a storm, remember, it's nowhere near its breaking point. It's just doing exactly what it was designed to do. So, why don't planes fall? Because engines don't keep planes up, momentum does. Because air becomes a solid structure at speed. And because thousands of engineers spent decades ensuring that even if everything goes wrong, gravity still has to wait its turn. So the next time you're flying and hear the engines throttle back, don't worry, you're just gliding.